Let's begin by drawing a model of the motion of the Earth around the Sun. So here in white is the orbit of the Earth around the Sun. The Sun is my yellow or no, red circle. And then in blue here is the infinitely large celestial sphere. And you can see that 23-degree angle of inclination of the polar axis with respect to the revolution axis. So on the celestial sphere, we can draw our NCP and SCP. We can draw our line, polar line here, and there's the NCP and SCP parallel to the axis of rotation of the Earth, and then cutting the celestial sphere in two in a perpendicular to the polar axis is the celestial equator. Now, this is the celestial sphere. All the stars are located on this infinitely large sphere. As we move around the Sun, now these different positions, we can identify this point as June 21st. How do I know? The north axis is pointing towards the Sun. And then over here is December 21st, and the direction of revolution is counterclockwise, meaning that after December, this is March 20th, and this is here in the back, September 22nd. Okay, so where is the Sun going to appear on the celestial sphere? Well, let's say this is December 21st. We would see the Sun in this direction here. So the Sun will be projected on top of the stars located here. And as you can see, this is south of the celestial equator by an angle of 23.5 degrees. When the Earth is in the position of the summer solstice in June 21st, the Sun will be in this direction to the left. And if we continue the projection, we would see the Sun over here. And this would be north of the celestial equator. Now we need a little bit of imagination to visualize this in 3 dimensions. But when the Earth is on March 20th, the projection of the Sun will be in the back of the screen and will intersect with the celestial equator. And then here, the position will intersect with the celestial equator, but in front of the screen. So that we can track down the position of the Sun in the celestial sphere over the course of the year. And as we rotate counterclockwise, so let's say we are in December, the Sun is here. This is the position of the Sun in December 21st. As we approach the front of the screen on March, the Sun will be approaching the back of the screen on the celestial sphere. So this is the direction of motion of the Sun around the celestial sphere over the course of the year, and this direction is also counterclockwise. So I repeat that the Sun is south of the celestial equator in December, north of the celestial equator in June, and intersect the celestial equator at the equinox, the fall equinox, which is on September 22nd, and the spring equinox, which is on March 20th. So this is where the Sun, and I just made the opposite here. Hold on. The Earth is here, March would be in the back, and September in the front. So this would be September 22nd, and the spring equinox would be actually back here. There you go. Let's make another diagram, this time only the Earth in the middle and the celestial sphere all around. And I will align the top with the NCP, the bottom with the SCP. Here's Earth's equator. Here's the corresponding celestial equator. And let's draw the meridians on the celestial sphere that correspond to the various right ascension circles. So the right ascension, as seen from the outside, increases from west to east. If we draw the celestial sphere with an observer, north, south, let's say somewhere in the northern hemisphere, and this is east and west, this is the equator, so you have an observer in the middle, we know that the right ascension increases towards the east. So if this is 20 hour of right ascension, then this will be 21 hour, this would be 22 hour, and in the back of the screen you would have the 23 hour right ascension. You increase by looking north towards the right, in other words, towards the east. But where is east and west when we look at the earth from the outside? We know which way is north. North is up here, and this is south. This is north, this is south. Well, if this is the earth, here's North America and South America, and this is Europe over here. East is to the right of the picture, as seen from earth, and west is to the left. So if Montreal is over here, then Vancouver will be to our left, and France would be to our right. So the right ascension increases towards the east. So if this is the 0 hour right ascension, then to the east we would have the 1 hour right ascension, and then the 2 hour right ascension, and so on. And on this side I would have the, so I drew the 0 hour here. Let's say this is the 23 hour right ascension, 22 hour right ascension, 21 hour, and so on. So it's increasing from west to east. And if you are an observer on Earth, you also increase the right ascension from west to east. So both agree, though they show different perspective. Now, why is this important? Now let's place the sun at its position on the vernal equinox, spring equinox. This is March 20th. The right ascension is defined as 0 at the position of the vernal equinox point. And this is where the sun appears to be on the celestial sphere on March 20th. Good. Let's go back to the previous picture. On the celestial sphere, the sun appears to go counterclockwise. And it starts on March 20th. This is at the back of the picture here. And then goes towards the summer solstice, which is June. And this would be north. So from the spring equinox, it is moving north of the equator, going counterclockwise. So up here, the position of the sun on the celestial sphere from the vernal equinox point, from March 20th position, would start to drift north of the celestial equator and reach the highest point on June 21st, 23° north, and the circle of right ascension that corresponds to this would be 1/4 of a turn. That's 6 hour right ascension. So the sun evolves during the year in the same direction as the right ascension direction. Okay, so the sun's position on the celestial sphere increases, and after 3 months, it's moved by 90° all around here to the 6 hour right ascension point, June. This is the northernmost point. From there, and this continues back of the screen, the sun will go back down and will cross the celestial equator again. That corresponds to the line of 12 hour right ascension. It's supposed to be at 12. So exact opposite March, that's September. And then continues towards the winter, and in December 21st would reach the southernmost point, And what is the right ascension that corresponds to this? That would be 18-hour right ascension. And then back to 24 or 0 March. This is Montreal, March 20th, spring equinox. You can see the blue line representing the celestial equator, and this purple or red line here represents the ecliptic. And you can see that the sun is crossing the equator line, and the sun is always on the ecliptic. Now let's speed up this animation and see what happens over the course of the day. I would like you to notice that the ecliptic is moving in the sky because the ecliptic is fixed on the celestial sphere and therefore rotates with the celestial sphere like everything else. And you can track a circle that represents the ecliptic all around the sky, and you can see that it's moving. So 12 hours later, so in the middle of the night, the ecliptic will have a different location in the sky than 12 hours earlier. Now, the sun, over the course of the day, doesn't move much. So this is the next day. You can see the sun is still more or less crossing the equator. So now let's see what happens, and this is looking south, after several more days. So let's speed up the time. So this is now, the date is April 12th. Now where's the sun? So compared to the equator, the sun has moved along the ecliptic. So this took a couple of weeks to move this distance on the ecliptic. And now the sun is north of the equator. If we look north, okay, maybe this is not so easy to see, but in any case, we should add the lines of right ascension. And now we can see that compared to the celestial equator here, the 0 hour right ascension, now we are in April, the sun has moved past the 1 hour right ascension. And if I continue several more days, now we are in May, the sun now has moved past the 2 hour right ascension point. And in June 21st, we'll be up here at the 6 hour right ascension. So the ecliptic describes a circle in the celestial sphere that is tilted relative to the celestial equator. And the sun moves around this ecliptic in the direction of increasing right ascension slowly over the course of the year, so that in the summer it is north of the equator and in the winter it is south of the equator. Here is the celestial sphere diagram of some random place in the northern hemisphere. If I want to draw the daily motion of the sun in the winter solstice, I would take the celestial equator, go south by 23.5 degrees, and draw a line that runs parallel to the celestial equator, and that would be the daily motion of the sun during the 24-hour. If I ask you what is the position of the sun when transiting, this will be the answer. Now if I was to ask you, draw the ecliptic at noon when the sun is transiting, you would have to make sure the ecliptic passes by the current position of the sun. You also want the ecliptic to make an angle of 23 degrees with the equator. So the ecliptic departs from the position of the sun, makes an arc which is tilted with respect to the equator and passes by the current position of the sun. 12 hours later, when the sun has set, so the sun now is in this position, the ecliptic would have turned and would be actually down here, and the ecliptic would make this angle. So the ecliptic turns over the course of the day.